All right. So today we'll get going here, talking a little bit about chemical equilibrium. Right. So before we do, we'll just do a quick review question on what we talked about last time. Kind of make sure. The concept we went over last time was binary mixture. So let's assume we are looking at a diagram, a phase diagram for a binary mixture where we're plotting pressure versus chemical composition, right? And the question is which of these is true, or potentially none of them, right? That the gas is the only stable phase above Raoult's law line. The y-coordinate of the lower line corresponds to the boiling temperature of the liquid mixture. The relative composition of one component increases from right to left on the x-coordinate, or none of these.
For B, are you talking about the y-intercept?
No, just the along that line for the lower curve, right? Any point along that line, if you go horizontally, connect to the y-axis, right? That value, the y value, corresponds to the boiling temperature.
I think it's 90. Yeah. Well, either C or 90. A, that's liquid.
Yep.
Right?
Yeah.
And B is also gas.
Gas.
Yeah, not liquid.
Is it? Are we talking about that curved one?
Yeah.
That's got gas. Right?
Yeah, so we're talking about like pressure versus composition, right? So yeah, so B, right, we're doing a pressure versus composition phase diagram. So it has nothing to do with boiling temperature, it has to do with vapor pressure, right? That Y component is related with vapor pressure, not necessarily with boiling temperature, right?
Doesn't C have to have a 2 component in order to do that?
Well, so C, I mean, right, so C is saying, right, that the composition, right, so the relative composition, meaning something like the mole fraction, right, of one of the components increases, and you go from right to left on the x-coordinate, which is technically true, right, for a binary system, right, because if the composition of what you're plotting is increasing from left to right, the composition of the other thing is decreasing as you go from left to right, so it's increasing from right to left. So, right, so C is a little bit designed to kind of be a kind of a trick answer here, right? Where normally you'd think, oh, well, the composition increases from left to right, but here it's saying that one of the components, right, doesn't matter which one, right, but at least one of them has its composition increasing from right to left, which is true.
Not the one we're plotting.
Yeah, exactly, just not the one you're plotting. So, but yeah, but if you kind of read that and thought of C as saying, right, that what you're plotting is increasing from right to left, then that would be false, right? Because what you're plotting is 0 and go to 1 for the chemical composition as we go from left to right. So the answer is C. C is true, right? If we're making a plot of a binary mixture of A and B, and on my plot I have the mole fraction of A, right? And as I go from right to left in my plot, the mole fraction of B will increase, right? Because as I go from right to left, the mole fraction of A decreases, therefore the mole fraction of B has to increase. All right. Any other questions? All right. So let's talk about equilibrium. Okay. I was debating if there's one or two little things on chemical equilibrium next week. I thought, well, I could potentially throw that in today, but and we're plenty ahead of time. So so next week on Monday we'll talk some about Le Chatelier's principle, and then we'll get into electrochemistry and talk about that as well, right? So again, so next week we're mainly doing electrochemistry, but we'll talk a little bit about Le Chatelier's principle and such next week on Monday. And then the week after that, which is the week before Thanksgiving break, that week we will talk about statistical thermodynamics and get more kind of into that kind of stuff. So, yeah. Today we'll just talk about chemical equilibrium, right?
So the next homework's due Monday.
Yep.
You have homework after that one?
This is homework number 5. So no, there is a short homework after that. That is, when do I have it marked when it's due on the calendar here? Maybe not. Oh yeah, no, I do. Right before Thanksgiving break, homework 6 is due. So sorry, it's just like kind of a week and a half or whatever between the two homeworks. Yeah. Yeah, I mean, so I made homework 5 due when it was because, like, yeah, I mean, there's a question. Basically, these last two homeworks, there's not quite 2 weeks worth of lecture material between them to be able to split up because we got kind of an exam in there and things like that. So, yeah, so I ended up, yeah, extending the deadline for this homework number 5, and then just homework number 6 is going to be a little bit of a shorter homework. But yeah, so there will be one more homework to do. So I want at least 6 homeworks because again, I dropped one homework for those who aren't aware, don't remember from the syllabus. One of the homeworks is dropped, so if you missed one, then you're fine, right? Obviously, I dropped the lowest scoring homework, not necessarily your highest scoring homework, right? That's going to be a jerk move to do, right? Drop the best thing. On Canvas, I have the option for any kind of grade item to drop the lowest and or the highest scoring thing. When I've never understood who would drop the highest scoring thing, but you know, I don't know. It'd be kind of
Yeah.
yeah, I don't know.
Teachers have it set up where their final exam is taken over 5 days, but you can't block it per student. Which can do that. So he'll drop that. If you take it twice, he drops your highest. And that's how he makes sure you only take it once.
I see.
He doesn't understand a 5 days. The final is 5 days long.
You can take it. Take it
Oh.
one
It's-
day of the 5 days.
Yeah, so it's open for yeah. It's open for 5 days for you to kind of do it and stuff. Yeah, I had I had to take home stuff last semester because it was like everything, doing it quick, and we for the PChem class, yeah, it was a take home exam. But so because it wasn't monitored and things like that, because it was just at the time not people doing it. It was open notes, but don't get too excited because then I made the exam more difficult because it was open notes. So so I promise that students who were able to use notes on the exams, their average scores did not really change from not being able to. So
They probably wrote all the equations, but didn't know how to use them.
yeah. But anyways, I digress. So let's see here. Oh shoot, I think I have not posted a participation quiz for this week, so I will post one today. I remember this time. So after class, I'll post participation questions for this week.
Change the answer on the last
I did. Hopefully, you check to make sure that if you feel like you answered the was like a colligative property question, put Kelvin instead of Celsius, that I marked you as correct. If not, feel free to email me and I'll double check and talk about it, right? But I should have fixed the last quiz answers. Yeah. So I think again. And then again, when we get closer, the annoying thing is, I don't know, maybe I'll try to take a poll online. I don't know. Maybe I just leave it up to the people who are attending class. But basically, like, I will give the option of potentially switching when the last exam is, whether it's on Monday or Wednesday, after Thanksgiving break. But I'll kind of poll the class to find out what people feel like with doing, and we'll see. So I don't know. Been real crap participation as of late, so I have no idea. Maybe for those who aren't showing up, they just don't get a say. We'll see. All right. So chemical equilibrium. Right. We should kind of have an idea of what chemical equilibrium is from other chemistry classes, right? Right. So which of the following is not a fundamental characteristic of a reaction at equilibrium? That it will be achieved regardless of your initial starting mixture. It will be equal moles of products and reactants. Temperature will be constant. Pressure will be constant. None of these things, right? All four. Right. Which of these is not true? So E, none, means they're all correct. F means 2 are incorrect. G means 3. H, all are incorrect. Right. So again, A through D, you're picking one of those being incorrect. If you think multiple are incorrect or none, then it's potentially answers E through H. Got someone online saying B. Yeah.
I have a feeling B is too, because you have to get more temperature in order to get some stuff at equal.
You assume.
Okay, yeah, okay, so yeah, I'll just say.
Yeah.
B, so C and D are correct.
Yeah. So
A seems correct. A is correct.
yeah, A is correct. I mean, you could kind of try to be a jerk about it. Well, if your starting mixture only included one of the two reactants, then technically it wouldn't reach equilibrium, right? But then you don't have a chemical reaction, and that's not really like a legit, answer a question, right? So yeah, so A is definitely true, right? That as long as you have some mixture of reactants, right, equilibrium will be achieved, right? No matter what, given enough time, right? Again, right? Thermodynamics, all we've been talking about this semester, right, is talking about what will happen given enough time. Now, enough time might be the life of the universe, who knows, right? But given enough time, equilibrium will be achieved, type of thing, right? We're not worried about how long it takes to get there, just that it will get there. Things want to get there, right? Things want to get to equilibrium. Things want to get to lower free energy, and so on and so forth, right? The universe wants the entropy to increase. It will do it, just might take some time to do so, right? So A is definitely true. B is false, right? Equilibrium does not mean equal moles of reactants and products, right? Equilibrium, right, can easily have different amounts of products and reactants when you reach equilibrium, right? If you're at equilibrium, right, temperature's got to be constant, because if you change the temperature, that's going to change your equilibrium, right? If you remember kind of Le Chatelier's principle or things like that, right, from Gen Chem, right, as well as pressure, right? Pressure's got to be constant, because if you're at equilibrium, right, you have constant moles of reactants and products, which means the pressure is going to be constant as well, right? So B is the only one that is false, right? So B is the correct answer here, okay? Right, so as just a review, right, kind of with our discussions of this, right, for those who maybe have long since tried to forget chemical equilibrium from Gen Chem, right? Chemical equilibrium, right, is a dynamic equilibrium, right? Equilibrium is established does not mean reaction stops. It just means the reaction of the rate of the forward reaction and the reverse reaction are occurring at the same rate, and they're equal. So you've reached equilibrium, right? To where there's no net change in moles of A and B, reactants and products. Okay, but reactants are still reacting and products are still forming reactants and so on, right? It's just that the total change in those concentrations stop. Okay, once equilibrium has been reached, right? Any questions about kind of this question?
Yeah, we have to use ice tables.
Potentially.
Yes.
Yes. There are, right. If we're dealing with equilibrium problems, you potentially need to use ice tables. Not, you can answer the question without doing an ice table, but I mean, it doesn't hurt to like organize your thoughts and ideas in something like an ice table. So, right. So just to kind of go in more depth about chemical equilibrium and why it's established and where it's established and such like that, right? We'll talk about kind of Gibbs free energy of a reaction, right? So we have some reaction here where I have some reaction coordinate, it is whatever it is, doesn't really matter, right? But it represents, right, at the 0 point of this reaction coordinate, I have all reactants at let's say 1, reaction coordinate equaling 1, okay? I have all products, right? And then somewhere in between, I have a mixture of reactants and products, right? Well, if the reactants and products are separated from each other, are not in the same container, right? You form products and it gets put in some other container, right? These aren't mixing, right? They are not mixing together. You just have reactants somewhere, products somewhere else, okay? Then the free energy for this reaction would follow the dashed line here, where it would just linearly decrease as a percentage of products increases until you get to all products, right? And every single reaction would go to completion, okay? Right? Every single reaction would go to the lower free energy state, whether it be products or reactants, right? If you're able to extract the products or the reactants, right, as the reaction is occurring. Okay? But most reactions, we don't do that, right? Most reactions don't extract the products as they're being formed, right? And so the reactants and products are mixing together, and because of this mixing, the free energy of the reaction as you're going along, going from reactants to products, is not the dashed line, right? But instead this solid curve where you have some extra free energy change due to that mixing, okay? See, I don't have that written here, right? But if you remember, right, for the mixing of a gas, right, right, if you recall, when we talked about mixing, number of lectures goes, right, the free energy change for mixing was roughly equal to the mole fraction of A, there's an RT out in front, mole fraction of A, ln of the mole fraction of A, plus mole fraction of B, ln mole fraction of B, right? Yeah, and there's like the RT out in front or something like that. And I think maybe it's like N total or something like that, I don't know. NRT where N is the total number of moles, I forget, right? But the main point, right, is it's related with, this expression in terms of the mole fractions of A and B, right? Right, which had a form, and there's a minus sign here, right? So the form of this, right, looked something like that, where the minimum here was at mole fraction equal to 0.5, right? And so in kind of the plot we had, this would be, say, like 0, and this would be 1, right? Okay. For our reaction coordinate, okay, if we pretend our reaction coordinate is the mole fraction of A or B, right, that I go from 0 to 1 to that mole fraction of, say, A, okay, the minimum is at 0.5, right? So you can imagine, right, that's effectively what is being done. Where am I going here? Right, on this curve, right, is effectively I have superimposed, right, this dashed line, and then another curve that kind of goes down around, I think, right, I can annotate, right? I can try to do this, but you know, I pretend, right, I have like something like this, right? Real rough, right? The red line here is that free energy of mixing that's occurring, right? And so I add kind of the dashed line and the red line together, and I get this green line, right? Effectively, okay? Right, and so because mixing is occurring and that mixing changes and lowers the free energy, right? The minimum free energy of your reaction is not when it goes to complete products, because when you go to complete products, you lose some of that entropy of mixing, right? You lose some of that entropy term, right? As you're going past kind of this midway point, right? As you're going down, your entropy is increasing, and then you get the equal mixture of the two things, and then your entropy starts decreasing, right? But, right, your products have a lower free energy, right? They may themselves have a greater entropy inherently than the reactants, right? They may have a lower enthalpy, things like that, right? And so, because of the difference in free energy of your reactants and products, right, your equilibrium is not at a 50-50 mixture of the two, but is favored towards the side that has a lower free energy in itself, okay, in this case being the products, right? But that entropy term does play a role such that, right, that entropy of mixing such that you will not go to full products, okay? Now, as the, you know, gradient, if you will, as the difference between the reactants and products free energy change increases, right? Right, if I had something, you know, like this, right, is the difference between the reactants and products free energy, right? That minimum would be closer and closer to the products, right? My minimum would be somewhere, say, out here with this level of change, right? If the equilibrium, right, if the reactants and products free energy was the exact same, right, then my minimum would be halfway in between, right? I'd have something, you know, kind of like that where the minimum's at, you know, 0.5, right? Right, which again goes along with the idea that we've seen in general chemistry, right, of, you know, the greater the free energy difference between your reactants and products, right, the more you favor, say, products or reactants, right? Okay. Right, and yeah, right, and so. And that's why you have, right, some reactions as effectively go to completion as we think about it, right? Well, other reactions don't, right? They maybe form just few products and mainly stage reactants, right? Your weak acids or KSP type equilibrium, right? Or you have equilibria that are somewhere in between, right? Where have maybe close to a 50-50 mixture of the two guys, right? And that's because the free energy difference between reactants and products is very minimal, right? And so the right where this equilibrium lies in terms of amount of reactants and products depends on the free energy, and we'll get to that dependence later, right, and show what that mathematically is, right, which you've seen it before in general chemistry, but we'll kind of derive it here, okay. But again, so this is why, again, this free energy of mixing is why, again, you don't get just full products for every chemical reaction, and there is some type of equilibrium established, right, where some amount of products and some amount of reactants do exist together, okay? Is, again, assuming these things are mixed together in the same thing. Okay? So questions about this concept, this idea, why equilibrium is established? Okay. So let's talk more about deriving where that equilibrium is established, right? Talking about that minimum free energy kind of more thermodynamically. Okay, so we'll talk about the extent of the reaction. I kind of been alluding to this, right? Which is, again, sort of the fraction of reactants that are reacted, okay? So again, when the extent of the reaction is 0, you only have reactants. When the extent of reaction is 1, you only have products. I'm going to consider a very simple reaction, A going to B, with stoichiometric coefficients A and B, right? So, right, if this is my reaction, okay, right, I can define, right, the number of moles of A at any point in the reaction as the initial number of moles minus the stoichiometric coefficient of A times the extent of the reaction, right? How much of the what percentage of the reaction has occurred, right? the number of moles of B, right, is in just the stoichiometric coefficient of B times the extent of the reaction, right? How far has that reaction occurred, right? What percent, right? 50%, 10%, 90, right? And then if I just take the derivative of these things with respect to the extent of the reaction, right, you get the change in number of moles of A is related with minus the stoichiometric coefficient of A times the extent of the reaction, and change in number of B's. Change in number of moles of B is just related with its stoichiometric coefficient B times the extent of the reaction, right? That's kind of fine, right? What I've defined here so far. Huh?
I forgot how to draw that. Yeah.
Oh, the what is that? Eta? I'm trying to remember. I think that's what that's called. Eta. Yeah, it's I what do I do when I try to draw Eta? Like, yeah, I don't know. You just kind of do some squiggly lines. Right, I'm not a mathematician, so I don't bother drawing it properly. But right, so this extent of the reaction eta, you could put alpha or whatever the heck you wanted for it, right? You don't have to draw eta, but anyways, right? Right, and that, again, this right should hopefully be relatively straightforward given the reaction above, right? And the stoichiometric coefficients A and B. Okay. So I'm going to define, right, the free energy change of my reaction, right, based off of what is the change in free energy with respect to the change in the extent of the reaction under constant pressure temperature conditions. Okay. Right, so that change in the free energy of my reaction as the reaction is going is related with what is the free energy change with respect to the change in the extent of the reaction. Okay, right. So right, I know, say, the change in free energy with respect to change in number of moles is related with the chemical potentials, right? Something we talked about before, right? That a free energy change with respect to change in number of moles is just related to that chemical potential, right? So dG is just mu A times dNA plus mu B times dNB. And I can relate these things with the extent of the reaction based off the equations above, right, from last slide, okay? So the change in free energy is equal to minus A times mu sub A d eta plus B mu sub B d eta, right? The change in the extent of the reaction, okay? And so I factor out that change in the extent of the reaction, right? And so I get that this change in the free energy of the reaction, okay, just related with the derivative of G with respect to the extent of the reaction, is just minus A, the stoichiometric coefficient, times the chemical potential of A plus B times the stoichiometric coefficient of B, okay? Right? And these chemical potentials depend on what the current composition is in your reaction, right? These things depend on how much reactants and products you have and such for your reaction, okay? Right? And then if I extended this to a reaction that wasn't just A going to B, right, there'd be some extra minus stoichiometric coefficient times chemical potential for reactants, an extra plus stoichiometric coefficient times its chemical potential for products, right? Right, hopefully it's relatively clear as to how you could generalize this for any reaction, okay? So, right, you're basically summing up chemical potentials times their stoichiometric coefficients and thrown in a minus sign if it's a reactant. Okay? Right, and so when equilibrium is reached, right, equilibrium is reached when your chemical reaction stops, right, and equilibrium is defined, right, when you've reached a free energy change for that reaction of 0, right? The minimum free energy, right? Again, as we showed in that previous slide, right, that minimum free energy is where equilibrium is reached, right? And we've talked about for changes in expansions, compressions of gases and things like that, right? That equilibrium, a reversible process, which is at equilibrium, right, has an entropy change of the universe equal to 0. And for constant temperature pressure conditions, right, the free energy change is equal to 0, right? For a process at equilibrium, right? So when our chemical reaction is at equilibrium, the free energy change of that chemical reaction has reached 0, okay, right? And so that implies, given the equation above, right, that the chemical potentials of the reactants equal the chemical potentials of the products, right? You just got to multiply by their stoichiometric coefficients, okay? right? And so that is when chemical equilibrium is reached, is when the chemical potential of your reactants and products are equal, essentially, right? Again, there's these factors of stoichiometric coefficients, okay? Because that's representing the fact that your reactants have like 3 of A or something like that and 4 of B. So you got to add in the chemical potential for each amount of A and each amount of B, right? Which is effectively just by multiplying by the stoichiometric coefficients, right? So again, that, right, the delta G that we're talking about is the change in free energy of the reaction that's represented kind of by this curve here, right? And so the minimum of this, right, where the slope is now equal to 0, that change in free energy with respect to the extent of the reaction is equal to 0, right, is where equilibrium is established. So questions about this far? Okay. Right. And so as your reaction is going towards equilibrium, right, in the forward direction, if you start with just reactants, right, the free energy change of that reaction is negative, and it's going to be spontaneous, right, to go towards equilibrium, right? When I've reached equilibrium, right, my reaction will then stop because its free energy change is now equal to 0, right? And at equilibrium, if I go to the right or to the left, right, see on this curve, right, if I go to the right or the left, right, my free energy changes and it increases, and that's going to be a non-spontaneous process. I'm not going to do it, right? If I start with just products, right, the free energy would change, right, and I'd go downhill as I go towards equilibrium as I start forming some reactants, right? So no matter what, starting with products or reactants, right, I will reach equilibrium, okay, and I'll reach that same point, which is the minimum free energy of that reaction, okay? Okay. But saying the delta G of the reaction equals 0 is not, right, don't get it confused with what we've talked about before with free energy changes for a chemical reaction and what you've seen plenty in general chemistry, right? What we've been talking about so far is the standard free energy change of a chemical reaction, right? Which the standard delta G, okay, for reaction is not typically equal to 0, right? But it is defined when the pressure is 1 bar for all gases, right? And the concentration is 1 molar for all aqueous, right? For all aqueous species, right? Right? Which that isn't what we're talking about. We're talking about delta G of the reaction for any potential pressure and concentration of your reactants and products, right? So delta G naught is for specifically at these conditions, right? Right, delta G of the reaction is any potential concentrations and pressures of reactants and products, okay? So those aren't referring to the same thing. So again, this isn't saying, right, we're not saying that at equilibrium, the standard free energy change, right, is equal to 0. We're saying at equilibrium, right, the free energy change for that reaction, given the current concentrations of reactants products, is equal to 0, right? Right, which those current concentrations and pressures of reactants and products are not guaranteed to be equal to 1 bar and 1 mole, right? Yeah. All right, so I have a vessel that's prepared by containing only reactant A. What is the sign of the instantaneous free energy change in the mixture 1 initially, and 2 when the mixture reaches equilibrium? What do people think? Oh, D, right? Yeah, right. This is going to be negative, right, initially, and then equal to 0 when you reach equilibrium. All right. So let's talk about then, say, for an ideal gas, right, what this equilibrium means, okay? Right, so for an ideal gas, the chemical potential, right, is equal to the standard chemical potential, right, which is the chemical potential at 1 bar plus RT times the natural log of the pressure of the gas at any pressure, right? And this is true, right, for any point in the reaction, right, for any extent of the reaction, right, that for the chemical potential of a reactant or product is always equal to this no matter where you are in the chemical reaction, okay, where P is the pressure of that gas, okay? Right, and so at equilibrium, right, the free energy change for the reaction is equal to 0, okay? So let's, again, consider this reaction AA going to BB, right? And I'm going to define the standard free energy change of my reaction, which we've seen before, right, as the free energy of B minus the free energy of A times their stoichiometric coefficients, okay? Right, which we've seen this before, right? The standard free energy, say, a formation of products minus that of the reactants multiplied by their stoichiometric coefficients, right? This definition here is nothing new. This is something we've come across before, seen before, okay? Right? And then again, at any point during the reaction, right, the free energy is just equal to the chemical potential of B times number of moles of B plus chemical potential of A times number of moles of A, right? Okay. But these are all kind of things that we potentially kind of discussed or talked about before, okay? And so again, we showed before that at any point during your chemical reaction, right, the free energy change of that chemical reaction is related with this quantity here, minus A mu A plus B mu B. So if I plug in for what the chemical potentials of A and B are, in terms of their standard chemical potentials, mu A naught and mu B naught, okay, right? And then their pressure of A and pressure of B, okay, right? I get this expression here that I get delta G of the reaction is minus A mu A naught plus B mu B naught plus minus A RT ln PA plus B RT ln PB, okay? Right? This first term, right, if we go back to the previous slide, right, this here, right, G and of B, right, the molar Gibbs free energy of B is just the chemical potential of B. So this is just the standard chemical potential of B, standard chemical potential of A, right? So this term here is just the standard free energy change of that reaction at 1 bar pressure, right? 1 molar concentrations, so on and so forth, right? And then here, what I'm going to do is we pull minus A into the exponent here. So I have PA to the minus A power, and then B goes into here, so PB to the B power, right? And then I combine the logarithms. So I just have RT ln of PB to the B power divided by PA to the A power, okay, right? And so this, right, is in general for an ideal gas, right, chemical reaction dealing with ideal gases, right? In general, this is the free energy change for that chemical reaction, right? That the free energy change of the reaction at any point is equal to the standard free energy change when the pressures of the gases all equal 1 bar plus RT ln PB to the B divided by PA to the A, which this should look familiar, right? Pressure or concentrations of products to the raised to the stoichiometric coefficients divided by pressure concentration of reactants raised to their stoichiometric coefficients, right? Which is your equilibrium constant, okay? We'll call it Q here for the, right, the reaction quotient Q, right, for when you aren't at equilibrium. But when you are at equilibrium, right, the total free energy change of that reaction is now equal to 0. And we say Q is now equal to K, the equilibrium constant. And so we get this relationship K, right? So this equals 0, Q equals K. And so you get that the free energy change, the standard free energy change of your reaction is equal to minus RT times the natural log of the equilibrium constant K, right? Which is just the concentration of products over reactants raised to their stoichiometric coefficients. Okay? Right? So we see, right, this expression for K and this relationship between free energy and equilibrium constant, or free energy and the reaction quotient, right? And standard free energy change, right? All of these things come back to how the Free energy changes with the pressure, which relates to then how the chemical potential changes with pressure, right? Right, and so that's where all these formulas come from. It's just based off of chemical potential, which is related with your molar free energy change, molar Gibbs free energy change, right, for your system. Okay. So questions about this equations here, and then this equation here, right? Questions about these guys? I guess this is the same as that equation in the last slide, right? Yeah.
So this says 2 equals K, does that mean like K would be given to us, or we would sort of calculate P?
Well, it depends on the problem, right? You might be given the value of the equilibrium constant. You might have to calculate the value of the equilibrium constant. So it just depends on the problem, right? You never have to memorize any. The only K that anyone's ever had to memorize, right? And actually, I don't know if you have to memorize Gen Chem. I guess it's given, right? The only K I actually remember is KW, right? The equilibrium constant for the auto ionization of water, 1 times 10 to the minus 14, right? It's the only one I actually know. All other Ks I'd have to look up, right? So you definitely don't have to memorize Ks. You wouldn't have to memorize KW anyways. I mean, we wouldn't use it really in this class, but we don't talk much about acids and bases. But yeah, so K is your equilibrium constant, right? You should know how to write the equilibrium constant expression for a chemical reaction. Hopefully, you guys have had enough practice of that in other classes, right? Feel confident doing that. Yep.
Why is the bottom equation delta reaction G not and not this?
Oh, okay. Yeah. Yeah, it's using this equation up here. Set Q equal to K. This term now equals 0 because you're at equilibrium. And so you just subtract this over to the other side. Other questions? Right. And again, this then shows you, right, how this relationship between, right, free energy change in the reaction under standard conditions, right? Because again, delta G R naught, right, is essentially the free energy of the products minus the free energy of the reactants, okay? Assuming, one pressure, one bar pressures for products and reactants and things like that, right? That this delta G R is related with, in that first plot we gave, right? In this very first plot here, right? It's this free energy change minus that, right? It's delta G here minus delta, it's G here minus G here, right? That's your standard free energy change, okay? Right? Okay. Here, right? So that's what that standard free energy change is, right? Which again, as we were talking about, right? The greater that difference is, the more that equilibrium lies towards the products, right? Assuming that the products are at the lower free energy, right? Which then again, mathematically, you can look here, right? When delta G is a very, very large negative number, right? Then K here has to be a very large positive number because the negative number here cancels that negative. So then you get like the natural log of K equals some big number. So K itself has to be a big number, okay? And K, right, is products of reactants. So that means you're favoring products, right? You got a lot more products compared to reactants, right? So as delta G gets more and more negative, right, the standard free energy change of your reaction gets more and more negative. Your reaction favors products more and more and more, right, at equilibrium, okay? Which is what we expect based off kind of the discussions and things like that we've had from the beginning, right? But again, the fact that K is not always right? The fact that this equilibrium is established is because we're allowing these things to mix, right? If you did not allow reactants products to mix, equilibrium would never be established, and all your reactants would eventually get used up until you got none left, right? And this is kind of, again, summing up the idea, right? Delta G naught is something we calculate from tables or things like that we've kind of done before, right? K is your equilibrium constant, right? Right, and specifically here, right? Use the subscript Kp, right? Meaning the equilibrium constant for pressures, right? Okay. Which is different from, say, like Kc, right? We use concentration for the equilibrium constant, right? If we have some reaction like this, right? You've potentially seen this stuff before in Gen Chem, right? Basically, you can use the ideal gas law to relate the concentration of a gas to its pressure, right? Related with RT here, and plug that in to get this general relationship, right? The Kp is related to Kc times RT is the change in number of moles of gas, right? And hopefully a lot of stuff we've talked about today, at least the punchlines, should be familiar, right? From things like general chemistry and potentially other chemistry classes you've taken. Okay? Whether or not, you know, where these equations come from aren't necessarily going to be familiar, but hopefully the final equations are something you've seen before. So again, right, for dealing with reactions that have gases in it, right, there is a difference between using Kp and Kc, okay? And it depends, right, on if you're using pressures for your gases or concentrations, right, as to which one you'd use and what they are, right? And the values aren't necessarily equal unless you happen to have the same number of moles of gases on your product side as you do on the reactant side. Then they will be equal. All right. Right, and just as a reminder, right, for writing these equilibrium constants or reaction quotients, right, we omit things like solids, liquids, right, the solvents in a dilute solution. And again, the idea here of omitting these things is just because their chemical potentials are not changing when you change how many moles you have of those things, right? So for a solid, right, its density, you know, its chemical potential is independent of how much you've used up of that solid, as long as some of that solid still exists, right? But again, for gas, its chemical potential depends on what the pressure is, right? Or for something in solution, its chemical potential depends on what its concentration is, okay? Right? The solute, its chemical potential depends on its concentration in that solution. And so those things have their chemical potentials changing as the reaction is moving forward and backward, right? But for solids, liquids, and solvents, their chemical potentials are basically staying constant during the course of the chemical reaction. So that's why they don't end up being included in your equilibrium constant expression. And they're just kind of lumped into the constant itself because those chemical potentials themselves are just staying constant, right? Essentially, it's, right, if I had, you know, this, right, if I had a reaction with, you know, A going to B, right, and if B was a solid, right, then its chemical potential would just be equal to mu naught, and that's it, right? It would just be its standard chemical potential. There wouldn't be this term that depends on pressure because it's a solid. And so, right, in here you would just have mu naught, and then this term wouldn't exist, right? And your equilibrium constant would just then depend on the pressure of A, which would be the only gas, right? So again, that's why, right, that's why things like solids and liquids don't appear, right? But then dissolved species or pressures do appear, right? When we use concentrations or potentially use activity, which is what we've talked about before, right? In these equilibrium constant expressions. Questions about this? Right. Again, right, just keep in mind, right, Kc for concentration, Kp for pressures, matter, right? Right. Technically, in this thing here, right, you got to use pressures of bar, right, for Kp, because this is standard 1 bar and so on, right? The difference between bars and atmospheres are very negligible, but. Right. Right. But yeah, but if you're dealing with gases, right, you're dealing with 1 bar type systems, right? What, not necessarily 1 molar systems, right? So you should use Kp instead of Kc. Okay. Right. But you're typically not given a problem where you have Kp and Kc for something. So you just use what K is given, right? But if for some reason you had both of those, right, you'd use Kp if you're dealing with gases in that calculation delta G. Okay? So the question of what is the equilibrium constant expression Kc for this reaction given here? It's going to be D, right? So the equilibrium constant expression is going to be D here. The water in this case is a gas, not a liquid. Okay, now often water is a liquid or a solvent, so you know I understand why you'd naturally not include it, right? But here it is a gas, and H2 is a gas, so we include both of those. And so it's products of reactants, and then we got to raise them to their stoichiometric coefficients, which happen to be 4. So D here is the equilibrium constant expression, right, for this reaction. All right. So a constant volume, constant temperature system is initially filled with 1 atmosphere of N2O4. If 30% of the reactant is dissociated at equilibrium, what is Kp? What do you think? You have an answer they like? Yeah, just do things in atmospheres. I guess if you're trying to pick with bars, don't worry about it. Some people are saying D. Anyone else get anything else? Oh, now saying B. So, right, we have this reaction. I forget what it was, but it's A going to like 2B. What the reactants products were, right? These are both gas. Okay. This is what N2O4 going to 2NO2. Yeah. So, well, whatever, doesn't really matter, right? Okay, we know initially the pressure of A initially is 1 atmosphere. Okay. Since this is a constant temperature, constant volume process, okay, that means, right, that think of our ideal gas law, PV equals nRT, right? Volume's constant, temperature's constant, right? So the change in pressure of the gas is related to the change in number of moles, okay? So if I lose 30% of A, that means at equilibrium, right, the final pressure of A at equilibrium, right, is 0.7 atmospheres. So I've lost 30% of A, right? So take off 30% of 1, that gives you 7, which means I've lost 0.3 atmospheres worth of A, which means that for B, right, I've gained 0.6 atmospheres worth of B because of the stoichiometric coefficient of 2 here, right? For every 0.3 I lost of A, I gained 0.3 of B, okay? And so then these are my final equilibrium pressures, right? And that Kp expression is then Pb squared over Pa. So it's 0.6 squared divided by 0.7, which gives you the answer A of Kp equaling 0.51. So questions about that? Right. If this was a constant pressure system, then the pressure of A would change because the volume would be changing, and it'd be a lot more complicated. Okay, because losing 30% moles of A wouldn't correspond to losing 30% of the pressure because the volume would change as well. Okay, right? But because we're leaving this as a constant volume, right? It makes it a lot simpler because then the change in moles is directly related linearly to the change in pressure. So 30% decrease in moles is the same as a 30% decrease in pressure. Okay. Right. I guess if you were to do this in a system where the total pressures remained constant, right? Then you'd have to calculate the number of moles you had of A originally, and then take 30% less of that, get the number of moles of B that you gain, get the total number of moles, figure out what the total volume is for the total number of moles of gas to maintain the total pressure of one, say, atmosphere. And then, given that, you can then calculate the partial pressures of your different gases and you know, using PV and RT and stuff. So it's a little bit more complicated. But.
So when do you use the KCRP?
If I ever need to convert between KC and KP, which is, you know, I present here. I don't think I have a homework problem that asks that. Maybe I have a random question here that asks it, but otherwise, let's see here. Calculate, no. Let's see, yeah, no. Yeah, it's just for converting the two. I just kind of give it, present it as given in general chemistry. Remind us where it comes from, but I mean, even in general chemistry, I don't really focus on it because I don't ever see the point of ever really using it much because typically you're either using KC or KP for your chemical reaction, depending on what you've measured for the reaction. So the conversion isn't really that important. But it might appear on like ACS final, I don't know. So, you know, but we're not taking it. So there you go. All right, so calculate the equilibrium constant Kp for this reaction here. At this temperature of 298.15 Kelvin, the standard molar Gibbs energy formation of ammonia NH3 here is 16.45 kilojoules per mole, right, for this chemical reaction, right? So given the stoichiometric coefficients in this balance. Oh, sorry, no, that's true. Right, this is delta G of formation of ammonia is this, okay, which this, as a hint, is not quite the formation reaction. Okay, so the free energy change for this reaction is not quite the same, but related to the free energy of formation of ammonia. Oh, shoot. Did I do that right?
That's why he needs that.
I actually messed that up. Well, if you get an answer, the correct answer is not actually listed here. And I do this, but we'll talk about it. Huh? You got D? So, unless I did my math wrong, D, I'll say right now, D is the only potentially possible answer from this. We can talk about that qualitatively, right? So while people are still working on the math, we'll at least talk about qualitatively, right? So, right, the reaction, right? Let's see if I can write that. The equation, right? Delta G equals minus R T ln of K, right? That equation, right? Or yeah, delta G naught. I just don't want to try to do the little naught thing with the mouse and stuff. So yeah, it is delta G naught of the reaction, and yeah, right. And so, right, the fact that delta G is negative means that this negative cancels with the negative in delta G, makes this overall positive, which means K has to be greater than 1. Okay, right? And so K has to be greater than 1, so it's either got to be B or D. And K, right, and the free energy change is not close to 0, so K is not going to be close to 1, right? When delta G, standard of the reaction, equals 0, then K would equal 1, right? So it's not going to be 1 here, or B. So D is the only possible potential correct answer. Now, if I did my math correct right now, and not before when I made these answers, then D is still wrong, but maybe I did my math wrong now and I did my math correct before, right? But, so how do we get this right? So the main first question is, right, main question to start with is, what is delta G of the reaction, right? And for this reaction, it's going to be 2 times the free energy of formation of NH3, okay? Because, right, this reaction that you're given, that you're asked for Kp specifically for this reaction, is twice, right, is a stoichiometric coefficient of 2 times the formation reaction of ammonia, right? The formation reaction of ammonia has a stoichiometric coefficient of 1 here. So I got to take 2 times delta G of formation to get the free energy change for this reaction. Oh, right? And I set that, so 2 times that free energy change for the reaction is going to equal minus 8.314 times 298.15 times the natural log of K, right? And then the only other trick here is this 8.314 is given in joules. This delta G is given in kilojoules. So you need to convert, say, joules to kilojoules or kilojoules to joules, right, to get the right answer. Okay. So, for example, B, or this answer, is only correct if you, so I put B here because B is basically if you didn't convert from joules to kilojoules, you would have gotten B, because you would have gotten, the exponent is very small. But, so the number I got is like 500,000 something. Yeah, something roughly around there. Yeah, exactly. So D is when you don't multiply it by 2. I should have multiplied it by 2, but didn't when I got this answer. So So D is the equilibrium constant for the formation reaction of ammonia, but this is not the formation reaction of ammonia. It's 2 times that, right? And if we recall, right, I mean, I guess just as a reminder, right, our manipulations of K, right, for equilibrium constants, right? If I have, right, if I have some chemical reaction, right, and I multiply it by a stoichiometric coefficient, right, so I get like n times my reaction, right, that means K is raised to the nth power, right? If I reverse my reaction, right, I flip it, flip the reaction, I have 1 over K, right? And if I have 2 reactions, right, that I multiply together, oh, it's not on there. Right, 2 reactions I multiply together, right, I multiply their Ks, right? People remember that from general chemistry, okay? So yeah, D is the square root of the right answer, because to the right answer, you multiply the overall chemical reaction by 2. And so D squared is actually the correct answer. But when I did the answer, I forgot about that and I actually got D. So. All right.
Would it be normal to have an answer that offered?
Yeah, I mean, so for chemical reactions with, you know, decent free energy changes of formations, right, we'll have very large equilibrium constants favoring the products, right? So yeah, so, you know, basically we typically don't do equilibrium problems where the equilibrium constant's very large because we just assume those reactions go to completion, right? You know, and so most equilibrium constants are that large. It's just we never calculate them or figure them out because they're so large that we just assume they're large enough things go to completion, right? We really only care about equilibrium constants that are small and things like that, because then we know they don't go to completion, right? And then we kind of care about how much product do we actually get. So, but yeah. Other questions about chemical equilibrium, why it's established, how it's established, the relationships that we have. Yep.
So the like from like the beginning of the slides, that like curve that you drew, can you just explain that one more time?
This curve?
So like you have this one, and then you drew like the
Yeah. Yeah, so basically, right, there's 2 things contributing to the free energy for this reaction as it's going, right? It's this dashed curve, right? This curve here, right? This is just, you know, this curve is roughly the mole fraction of, say, A times the, you know, delta G naught of the reaction, right? The standard free energy change of the reaction times like the mole fraction, right? If I assume my x-axis here is like the mole fraction of A, right? Right, that's effectively what that dashed line curve is, right? It's just like, right, how much reactants times their free energy plus how much products times their free energy, right? Type of a thing, right? So it looks something like this, right? You know, I mean, it's plus like, you know, it's got a y-intercept and blah, 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 blah. But roughly that slope is related with the standard free energy change of the reaction times, right, say the mole fraction. And then the other thing that's affecting the free energy is the fact that, again, if I'm plotting, now the scale isn't the same, right? So I have like 2 axes here, right? So the purple curve, right, has a different y-axis than the red, right? The red y-axis goes 0 here, 0 here, and then, you know, some minimum delta G here that's negative. Right, where its minimum is at 0.5, right? And then again, the purple curve, right, its y-axis is given over, you know, on the left side, right, which is, you know, whatever these values are, right? But so I'm trying to kind of superimpose these 2 curves, right? And then the fact is that it's, right, it's these 2 free energy changes are adding together because I have the free energy change of just like reactants going to products, assuming no mixing, plus the free energy change of mixing gives us the total free energy change for that chemical reaction. And so the sum of these 2 curves gives us this curve here roughly. And if I were to plot things correctly and blah, 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 right? Assuming kind of ideal mixtures and such.
So the dotted line is no mixing.
Yep.
Curved line is mixing. And then the line that we have is.
Yeah, the red line that I drew. So, oh yeah, so the red line I drew is just purely mixing, assuming no chemical reactions, right? The dotted line assumes just chemical reaction, no mixing, and then the solid black curve is chemical reactions with mixing.
Oh,
Right. Other questions? Right, and again, the fact that this free energy change of mixing isn't that large, right, at like standard temperature conditions, right, standard temperature pressure, right, is why the equilibrium is mainly dominated by which side has, a lower free energy, right, as to where the equilibrium lies, right. If you get to high enough temperatures, then that mixing becomes a little bit more important and things like that, right, and then it's less important what the free energy change is between your reactants and products, right? And that the equilibrium will lie more close to an equal mixture of the two. Okay. All right. So.
Will it ever get, and will equilibrium ever be 50-50?
Right. So if we go to this annotation stuff, so if we go, oh shoot.
I remember saying all of the reactions had the exact same thing when the
Right. So basically, if T is like infinitely large, right? I divide T over here. I get some number divided by infinity. This is effectively 0. ln of K is equal to 1. So every reaction, when you go to high enough temperatures, will have an equilibrium constant equal to 1. And next time we'll talk about the dependence of the equilibrium constant on temperature. But yeah, so any chemical reaction, technically its equilibrium constant will go to 1 as temperature goes to infinity, right? Now, if your equilibrium reaction has an equilibrium constant close, right, and an equilibrium constant equal to 1 means that you have like potentially equal amounts of products and reactants, right? If it's a binary system, you have to have equal amounts of products and reactants, right? If it's not binary, right, and you have multiple things, then it could not necessarily be that all have equal moles, right? But the product of those things, right, you have to like, the ratios have to be the same. But yeah. So in terms of having equal moles will depend on equilibrium constant. Oh, the heck. Depend on the equilibrium constant, right? And technically, you could have an equilibrium constant that isn't equal to 1 that could have at equilibrium, right, equal pressures of your gases, right? It's just that you have some pressures that are squared, some that aren't, and things like that, right? And so the equilibrium constant, it should, it doesn't have to equal 1 for the pressure to be equal. But that, those are rare cases and things like that. But in terms of the equilibrium constant being equal to 1, that's only occurring either in chemical reactions that have essentially no free energy change or are at extremely high temperatures. Right? Then the mixing term is the most dominant term. Any other questions? All right. So that's it for today. For those on Zoom, if you have any other questions, I'm happy to answer them now. Otherwise, I'll close out the Zoom session. Doesn't seem like I'm getting any, and actually it looks like basically everyone left. So see you guys Monday.